Okay, so when we think of evaluating a function, we can think of our definition of f of x, like for example, 3x squared plus x minus 5. We can think of our variable x as a placeholder, or maybe saying, for instance, if your x is your input, here's what the function does to x. Okay, so think of x as an example. You know, we're actually using it generally, but saying for all x would be all of our inputs. Okay, but we can take that x out and say, let's just put blank parentheses there. So we can say f of blank equals 3, and every time you see an x, put blank parentheses. So f of x equals 3x squared plus x minus 5. We can think of that as f of blank equals 3 times blank squared plus blank minus 5. So for example, let's say we want to look at f of minus 1. We can just put minus 1 in those blank parentheses. Okay, minus 1 there. Okay, minus 1 there. Okay, and then when we do the blank parentheses and just insert whatever we're taking the value of the function at, then it's easy to do. So 3 times minus 1 squared is 3, minus 1 would be 2, minus 5 would be minus 7. So we can say f of minus 1 in this case equals minus 7. So it's helpful to use the blank parentheses, you know, take the x out and put blank parentheses every time you see an x. So kind of know what to do when you put other things into the function besides x. So let's look at f of minus 2 for this function. So here I have the blank parentheses, but I put the minus 2 in there instead. So f of minus 2 is 3 times minus 2 squared plus minus 2 minus 5. Okay, so minus 2 squared is 4. So 3 times 4 is 12. Minus 2 is 10. Minus 5 gives us 5. Okay, f of 0, I put parentheses in here, but 3 times 0 squared is 0. Plus 0 is 0, and then minus 5 is minus 5. Okay, f of 4, 3 times 4 squared is 3 times 16, which is 48. Plus 4 is 52, minus 5 is 47. So you can see, actually let me put the parentheses there so we can see that we're putting, you know, 4 wherever we had our blank parentheses for f of 4. Okay, f of 1/2, do that again, is that we're putting 1/2 in our blank parentheses. So 3 times 1/2 squared, 1/2 squared is 1/4, so 3/4 plus 1/2 would be 5/4. Okay, and then minus 5 would be minus 20/4. That would give us minus 15/4. Okay, so here we're putting 1/2 in. Okay, and when you do something with fractions, keep it as an improper fraction. Don't write it as a mixed number or a decimal. Okay. Okay, and remember that the domain of a function is the set of all inputs for the function. Okay. Now we might state this explicitly, so maybe we want to limit our domain. Now normally if we just looked at this function f of x equals x squared, we could say x can be any real number, right? But maybe we want to limit it for some reason. So in this case, maybe we just want to say numbers, any real numbers between 0 and 5, including 0 and 5. So this is an artificial restriction, but maybe we want to say that, you know, say that we're only going to look at the numbers between 0 and 5. So you can limit the numbers that you use, okay? Okay, if the domain is not stated explicitly, okay, then we use the set of all real numbers for which the expression is defined as a real number, okay? In other words, any x that works, okay? So if looking for this first function, f of x equals x minus 4, think of where this is defined for real numbers, for x, okay? And the only place it's not defined is when x is 4, because we can't divide by 0, okay? So for this one, we would say our domain is, we could say x is not equal to 4, right? And that implies all real numbers except 4. Okay, so when we say this, we're saying, okay, all real numbers, but x can't be 4. Okay, and the reason is because you can't divide by 0. So when the domain is not stated explicitly, we figure out which x's work, and we include those, and then we figure out which x's don't work, and we exclude those. So the only x that doesn't work here is 4, right? For g of x equals square root of x, we could say, well, you can't have a negative, right? You can take the square root of a positive, but you can't take the square root of a negative, and you can take the square root of 0. So here our domain would be x, x would be greater than or equal to 0. Remember, we can take the square root of 0. Okay, so here we would just say x can't be negative, or x is greater than or equal to 0 would be our domain. And that means all real numbers that are positive or 0. Okay, let's look at some other examples. Let's say f of x equals x squared minus 1 over x squared minus x. Now we can't have 0 on the denominator, so we have to look at where x squared minus x is equal to 0. Okay, so we want to see where x squared minus x equals 0. And then when we factor, we get these, x equals 0, x equals 1. So that would be the numbers that we cannot use. Okay, so our domain here would be, now we're applying all real numbers, and we'll say we can't use these two. So x is not equal to 0 or 1. Okay, and the reason for that is because when you have 0 or 1 for x, you're going to get 0 down here, and you can't divide by 0. And we did that by factoring that denominator and setting it equal to 0. Okay, so for part A, the domain is formally the set of all x such that x is not equal to 0 and x is not equal to 1. Okay. Now we can also use interval notation. This should be a minus infinity here. Okay, so it's minus there. Oops, don't want to do that. Okay, minus infinity. There we go. Okay, so think of our interval starts at minus infinity, goes to 0, skips 0, so we go 0 parentheses, union. Then we start after 0 again, so we got 0 parentheses, and we go to 1 parentheses because we're skipping 1, union, and then we start after 1 again, so we have 1 parentheses going to infinity. So you can see this is where our cuts are, at 0 and at 1. Okay, that we're not going to include 0, we're not going to include 1. So yeah, it's a little bit more complicated to write it with interval notation, but you see we just put the numbers that we're skipping in between, and we don't use brackets. Okay. All right, B, we had f of x equals square root of 9 minus x squared. Make that g of x. So g of x is the square root of 9 minus x squared. Now remember, whatever's in the square root has to be positive or 0. So 9 minus x squared is greater than or equal to 0. Now this is a nonlinear, say x squared, inequality. So remember what we have to do here. We have to factor. Okay, so we have 3 minus x times 3 plus x. This is the difference of squares. Okay, and set it equal to 0. And then we get x equals 3 and a minus 3. Remember, we have to use our key numbers there. So we're doing the key number thing. And we're going to set up our intervals. So we have 0 here. We have 3 here. We have minus 3 here. Okay, so these are our key numbers there, there. And remember, we have to set up our intervals. So we do this, this, and this. Okay, and then we pick a number in each one. So if we try, let's say, minus 4 here. Minus 4, 3 minus minus 4 is positive. Okay, and 3 plus minus 4 is negative. So this is going to be negative here. Okay, if we try 0 here, let's try 0 there. 3 minus 0 is positive, and 3 plus 0 is positive. So this is a positive. Okay, this interval. And then if we try 4 here, 3 minus 4 is negative. Okay, and then 3 plus 4 is positive. So negative times a positive is a negative. So remember, we have to get the sign of each interval. Okay, and we're looking for this thing to be greater than or equal to 0. So we want it to be positive, right? So we're going to use this interval, which is between 3 and minus 3 and plus 3. So that's how we get this interval. So it's a little more complicated than it looks, right? We have to do that thing that we did in chapter 1 where we did our nonlinear inequalities. So we have to factor, set it equal to 0 and look at intervals in between those points and on the outside of those points. Okay, so this would be our solution. Minus 3 to plus 3, and we include the endpoints because we're including equal to 0 there. Okay, so this domain is a little bit more complicated. Okay, so there's our domain, is this thing right here. Set of all x such that minus 3 is less than or equal to x, which is less than or equal to plus 3, or we can just write it as minus 3 to plus 3 with brackets as an interval. Okay, our last example was h of t is t over square root of t plus 1. This t is fine, but we have to make sure that t plus 1 is greater than 0. Now, I don't have greater than or equal to 0 because we have it in the denominator, right? So if it was just a square root by itself, we could say t plus 1 is greater than or equal to 0. But because it's in the denominator, it can't be equal to 0. So we have t plus 1 is greater than 0, so we can just say t is greater than minus 1. So this would be our domain for this function, would just be t, set of all t such that t is greater than or equal to minus 1. That way we get a positive in this square root. We can't get a 0. Okay, so generally we can describe a function in 4 ways. Verbally, using a description in words, which is what we kind of did at the beginning. We don't do that, that often. Algebraically, by using a formula, that's most common. Visually, using a graph, or numerically by showing a table of values. Okay. So here's an example of how we describe a function using words, going from Fahrenheit to Celsius. To find the Fahrenheit equivalent of a Celsius temperature, multiply the Celsius temperature by 9/5, then add 32. So that's a verbal description of how we go from Celsius to Fahrenheit. Okay. If we were to do this using words or using algebraically, we could say F equals 9/5 times C plus 32. So that would be the algebraic equivalent of that. We're taking 9/5, multiply C times 9/5, and then add 32 to get our F. Okay. This is our input or independent variable, and this is our output or dependent variable. Okay, so we talk about the area of circle as a function of its radius. We could write, now notice we have this notation here with R in the parentheses. That's saying area is a function of radius. That means radius is our input, okay, and then area is our output. So area is a function of radius is pi times r squared. Okay, so sometimes you'll see this notation, and it kind of, the equivalent of that might look like this, and we don't use this a lot, but we could say y is a function of x. Okay, let's say this would be x squared plus 4. This says y is a function of x, and to get y, you take x squared and you add 4. X is our input. Normally we would write it as a function generally like this, f of x equals x squared plus 4. So that's kind of the analog to this using x and y. But this is a little bit awkward. This does not mean y times x. This means y is a function of x. Okay, and we take x squared plus 4. And normally we don't put that x there. We just write y equals x squared plus 4. And we can do the same thing here with this area. We could just write a equals pi r squared. So just keep in mind that these represent the same thing. Okay, and this would be the same as y equals x squared plus 4. Okay. So we could say the graph produced by a seismograph is a visual representation of the vertical acceleration function of the ground during an earthquake. So that might be a visual representation of a function. Consider the function C of W, which is described verbally as the cost of mailing a first-class letter with weight W. So here weight would be our input and cost would be our output. So here's just some summaries of the 4 ways. So verbally, we can use words, convert from Celsius to Fahrenheit, multiply the Celsius by 9/5, then add 32. And then algebraically, we did area of a circle, A of r equals pi r squared. Here's our seismograph where you can see as we go left to right with our acceleration as time goes by, so this is time, and vertical acceleration during earthquake, it would be, you'd see the little needle that would draw this, so you can think of that up and down as the function, okay, as time goes by, and kind of, marking the seismic activity there. And here's table of values. So this one might be your cost for mailing a first-class letter. So when your weight's between 0 and 1 ounce, your cost is $1.22. When it's greater than 1 but less than or equal to 2, you can say it's $1.39. When it's between 2 and 3 ounces, it's $1.56. Between 3 and 4 ounces, it's $1.73. And between 4 and 5, it's $1.90, etc. Okay, and it's actually, you can see it's going up 17 cents every time. Okay, that would be our slope. We'll talk about that in another section. Okay, so notice it doesn't include 1 here. So if it's 1, it's going to go in the first category. If it's 1, if it's more than 1, it'll go in this category. If it's 2, it's in the second category, but if it's more than 2, it goes to the third. Okay, just notice that we have less than's here and less than or equal to is there. Okay, our last example, F of C is a Fahrenheit temperature corresponding to the Celsius temperature, C. So F is a function that converts Celsius to Fahrenheit. Okay, so we looked at that box above, but find a way to represent this function algebraically, numerically, and visually. We already did this one, but algebraically we would say F of C, that's F of C, is 9/5 C plus 32. So we're going to take C multiplied times 9/5 and add 32 to get our F. Okay, and then here's a table of values, and we're just using different values. So here we had C is 0, F is 32, C is minus 10, F is 14. Okay, when C is 10, it's 50, F is 50, C is 20, F is 68, when C is 30, F is 86, etc. Okay, so just a table of values. We're not using all the values, but we're using a certain number of them there. Okay, and then finally, this would be a graph of our functions, our function F and C. So here's C is our input, that's like the X, and F is our output, that's our Y, and this would be our y-intercept is when C is 0. So when C is 0, F is 32. And then our slope, actually, if you look at that slope, our slope is 9/5. So as you go across 9, let me do it here. As you go across 9, you go up 5. Okay? And we can see that our F was 9/5 C plus 32. There's our y-intercept, our B, and this is our slope, our M. Okay, we can see the slope there. As you go across 9, you go up 5. Across 9, up 5. Across 9, up 5. Okay. Or backwards, we can go, as we go back, minus 9, down 5. So minus 9, minus 5. Minus 9, minus 5. Okay, and the last thing I want to talk about in terms of defining a function, which we'll talk about a little bit more in class, but you can also think of a function as a set of ordered pairs where each input x has exactly one output y. So we can say a function is a set of ordered pairs where each input x has exactly one output y. And another way to say that is that there's no repeated x. Okay, so let's look at a few quick examples here. Here's my set of ordered pairs. I didn't use set notation, but let's say we have these 3 ordered pairs. Okay, now each input has exactly one output. So the input of 1 is an output of 2. Remember our ordered pairs are looking like this, x comma y. So the x is always first. Okay, and then so 1 goes to 2. Okay, input of 2 has an output of 3, and input of 3 has an output of 5. Each input has exactly one output. Okay, so here we could say our domain is using set notation, 1, 2, 3. Okay. Our range is 2, 3, 5. And here I'm just pointing to the outputs here, 2, 3, and 5. Okay. The second column is not a function, and the reason is because the input 1 gives you 2 outputs. It gives you 2, and it also gives you 3, right? So this is not a function, so we wouldn't define that as a function at all. Okay, so let's cross that one off. Okay, I put a little x there. Okay. And then the last one, it looks like it may not be a function, but it actually is. Remember we said, and notice going back to the second one, we do have a repeated x there. We have 1 twice. Okay. Now 1 gives us 2, 2 also gives us 2, and 3 also gives us 2. That's okay. It's still a function because think of the definition where each input has exactly one output y. Well, 1 has exactly one output, it's 2. 2 has exactly one output, it's 2. Doesn't have to be unique, right? And 3 has exactly one output, it's 2. So it's the same output for each one. That's okay. You can have repeated y's, you just can't have repeated x's. Okay, so there's no repeated x's here, so this is a function. So domain here is 1, 2, 3 again. Okay. And the range is just the number 2. Okay. Now, if we were to graph these two functions, show them graphically, we would just have three dots. Here's 1 point, 1 point, 1 point, and this would be three dots too, and these would line up horizontally but not vertically. Here you'd have 2 points that line up horizontally and line up vertically, and you can't have that. So we'll talk about that in the next section.